Hi, in this video we are going to go through some worked examples solving simplified real-world problems using matrix inverses. We'll start off with an industrial production problem. In summary, you can read through the problem yourself, but I will sort of summarize the situation. We have a number of students starting up a company making submarine drones, submersible drones, that they're selling for people interested in underwater photography, and are currently trying to sort out how to address uncertainty in their supply chain or variations in their supply chain with their production targets. They have already implemented their designs. They have 3 models that they're planning on producing. All of these are going to use exactly the same external body, but will differ in internal design. They'll have a light version with a single propulsion unit and a single camera, a pro version with 2 propulsion units and 2 cameras, allowing it to move forward and backwards and to view forwards and backwards, and a higher end version that also has 2 propulsion units but has a 3rd camera added in such a way that almost omnidirectional viewing is possible, viewing in all directions. They're very concerned about producing things with no waste, that is, using all of the materials that they obtain, all of the supplies they order, because of concerns about cost and so on. So if they are able to make a supply order of 500 bodies, 1,000 propulsion units, and 1,200 cameras, what would the distribution of models that they produce be in order to perfectly use up this supply chain? If the body production was more efficient or more cost effective, and so they were able to get 600 bodies instead, how would those targets change? If the camera supply was maybe decreased, perhaps in addition to this increase in body target, so that we had 1,100 cameras, 600 bodies, and 1,000 propulsion units, how should their no waste target be adjusted? These are specific examples. What about the more general question of how does a difference in supply, say a 10-unit difference in supply of any one of the individual components, affect these ideal production targets? I recommend that you pause at this step and work through the problem before resuming the video. The first step in a problem like this is always formulating the mathematical model, and an important first step in formulating a mathematical model is defining the variables. In this case, one of the key unknowns is how many of each unit should be produced. We'll set xi to be that value, where I equals 1 for the light version, I equals 2 for the pro version, and I equals 3 for the pro X version. However, unlike the problems that we've looked at previously in the introductory unit, in the unit on formulating things in the language of matrices, in the unit on Gaussian elimination, in those cases we had generally a single supply value to work with and trying to solve the problem for that. In this case, we have multiple supply totals, as well as uncertainties in the supply total. Right? This is going to change how we address the problem. It means that we need to be formulating this problem using symbolic constants for our right-hand side, rather than having simply numbers in place there. That will define Bj to be these the symbols we use for these constants. Again, making a distinction, we use x because this is really an underlying variable in the model. We use B, a letter early in the alphabet, because it's a constant, but it's a constant that we want to be able to change with different instances of the model. J equals 1 will be for bodies, 2 for propulsion units, and 3 for cameras. This leads to a set of 3 equations, one for each component, where the left-hand side has the amount we need, the amount that are needed in order to produce the targets. So, and the right-hand side has the available supply. And we'd like to make these perfectly equal for the no-waste solution. So for bodies, every one of the units uses a single body. So we have x1 plus x2 plus x3 on the left-hand side. For propulsion, the light version has a single propulsion unit. The Pro and the Pro X both have 2 propulsion units. We get x1 plus 2x2 plus 2x3. For cameras, the light version has a single camera. The Pro version has 2, and the Pro X has 3. So we have x1 plus 2x2 plus 3x3 on the left-hand side. And the right-hand side has our symbolic constants for the total available bodies, propulsion units, and cameras. This is our systems of equations form. We can easily recast this into matrix form, AX equals B, with a coefficient matrix A that has all ones in the first row, 1, 2, 2 for the second, and 1, 2, 3 for the third. X is, of course, our variable of X of numbers produced, and B is our vector of supplies. One way that we can solve this in a general way for many different right-hand sides is to take advantage of the matrix inverse. As long as A is a non-singular matrix, we note that it's square, then if we can compute the matrix inverse, then X equals A inverse B will give us an answer. If we compute this ahead of time, we can simply plug this in for any different B we're interested in and move forward from there. So our first step becomes compute the inverse for this coefficient matrix. Let's walk through that process here. We start, as always, for Gauss-Jordan elimination to compute a matrix inverse by setting up a block matrix that contains A in the left-hand block and the identity of the same size in the right-hand block. So our A matrix and our identity. We then follow through with standard Gaussian elimination, forward elimination, and back substitution. Starting with the upper leftmost entry, use this as a pivot to eliminate downward. Coefficients are all the same, so we simply subtract the first row from both the second and the third. For the second row, 1 minus 1 is 0, 2 minus 1 is 1, 2 minus 1 is 1, 0 minus 1 is negative 1, 1 minus 0 is 0, and 0 minus 0 is 0, giving us our second row. And for the third, 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, 0 minus 1 is negative 1, 0 minus 0 is 0, and 1 minus 0 is 1 for our second row. We then move down and to the right to our next pivot, and again use this to eliminate downward. Same coefficients, so we subtract the second row from the third. 1 minus 1 is 0, 2 minus 1 is 1, negative 1 minus negative 1 is 0, 0 minus 1 is negative 1, and 1 minus 0 is 1 for this third row. At this point, we have 3 pivots, all with zeros to the left. This is our upper triangular form. They're all 1, so we don't have any scaling to worry about. We move forward with back substitution, eliminating upwards, starting in the bottom row and eliminating up through this column. Coefficients are all the same, This problem has been set up so the arithmetic works out very simply. So we simply subtract the third row from both the first and the second. 1 minus 1 is 0, 1 minus 1 is 1, 0 minus negative 1 is 1, and 0 minus 1 is negative 1 for our first row. The second row, 1 minus 1 is 0, negative 1 minus 1 is negative 1, 1 minus negative 1 is 2, and 0 minus 1 is negative 1 for our second row. After eliminating with that pivot, we move up and to the left to our next pivot, and again eliminate upwards. Once again, same coefficient, simply subtract the second row from the first. 1 minus 1 is 0, 0 minus 0 is 0, 1 minus negative 1 is 2, 1 minus 2 is negative 1, and negative 1 minus negative 1 is 0. This gives us our last row. We now have the identity matrix in our coefficient block, which means that this second block contains the inverse. Now we've computed the inverse, we can go forward and see how we can use this to answer the questions in this problem. So let's tackle the first one. The first one, if the suppliers are able to provide 500 bodies, 1,000 propulsion units, and 1,200 cameras, what's the no-waste solution? All we do is we take our general solution of x equals A inverse B, where we've just computed A inverse. This is our inverse from the previous screen. And we construct a B using these values, 500, 1,000, and 1,200 for B1, B2, and B3 respectively. Then go through and do the matrix multiplication. For the first entry, 2 times 500 minus 1,000 gives us 0. For the second entry, negative 500 plus 1,000 minus 1,200 is 2,000 minus 1,700 is 300. For the third entry, 0 minus 1,000 plus 1,200 is 200. This supply would allow production of 300 of the Pro units and 200 of the Pro X units with no waste, but with no production of the light version. This is probably not what they were hoping to do. It's unlikely they would have developed plans for 3 models if they don't intend to produce one of them. So this is not a good choice of supply inputs for a no-waste solution. So perhaps they ask, well, what happens if we can increase the number of bodies? Maybe that would allow us to make some of the light version as well. You might think this is a reasonable response. What does the light version use sort of the least of? It uses the least of the cameras and propulsion units of all 3, so maybe just bump up the number of bodies. Bodies are also probably cheaper than cameras and propulsion units, and so maybe it's a place to look for variation. So how would we look at this effect? We could plug in that result. The only thing we change compared to the last problem was changing this first entry to a 600. If we do this, this first row now becomes 1,200 minus 1,000, 200. Great. But look at what happens in the next rows. The second row becomes negative 600 plus, this is an incorrect solution here. So sorry here, I will correct this on the slides. Negative 600 plus 2,000 minus 1,200 is clearly not negative 400. That gives us 2,000 minus 1,800, which is 200. A balanced production, getting 600 units here, would give a balanced production of 200 of each type. All right, so we see that a very modest change in the supply, increasing the number of bodies by 100, gives a much more balanced overall production scheme. What happens if there's other variations? What happens if perhaps they've now set themselves on this target for a balanced production scheme and their camera supplier tells them, you know what, we can't produce 1,200 cameras for you, we can only supply 1,100. How would this change their production targets? Again, what do? We can simply add in a second adjustment, putting 1,100 in this last entry, and recompute the vector. For the first, we have 1,200 minus 1,200 minus 1,000 is 200. It's not affected by this change because of the 0. For the second entry, we have negative 600 plus 2,000 minus 1,100. So that's 2,000 minus 1,700, 300 units. And for the last, we have 0 minus 1,000 plus 1,100, or 100. If they have 100 less cameras available, the right solution is to transfer 100 unit of production from the Pro X into the Pro, and that will satisfy all of the equations. Right? These were some examples just with final targets in place, where we resolve the problem and then see what happens. You might think a much more productive way is to look at how does each variation in supply change each component. How should they be able to respond in a dynamic way if they find out that they have a few more of one or a few more of another in certain supply areas? Right? We might phrase this with this last question of how does a 10-unit difference in supply of each component affect these ideal no-waste production targets. We can also do this with the inverse, taking note that a difference in a right-hand side, represented by a b plus delta b, can be related to a change in a solution, x plus delta x, by solving the problem with the inverse, and then recognizing that the original solution x was given by A inverse B, so the difference in the solution is A inverse times the difference in the right-hand side. That means that we can address this question by simply creating 3 separate difference vectors, one changing only one unit, one type of supply value, by 10, and leaving everything else as zeros. We then can figure out what the delta x for each of these is, simply by plugging this vector in, multiplying by the inverse. 20 for the first, these are going to be very easy because of all of the zeros. So essentially what is going to happen here is that the first column is going to be pulled out, multiplied by 10, 20 minus 10 and 0. This, because we have 0, 10, 0, the second column is going to be pulled out, multiplied by 10, negative 10, 20, negative 10. And for this case, where the third entry is the non-zero one, the third column will be pulled out and multiplied by 10. 0, negative 10, 10. So increasing in body supply can be adjusted, can be accounted for by increasing the light production targets by 20 and decreasing the pro production targets by 10. A 10-unit increase in propulsion supply can be accommodated by decreasing by 10 both the light and the Pro X versions and increasing the Pro production target by 20. A 10-unit increase in the camera supply can be accounted for or handled by decreasing the production of the Pro version and increasing the production of the Pro X version, each by 10. Decreases would simply change the sign of this. Combinations of different quantities of change would simply scale the values. A 20-unit increase would just double these values, for example. And changes in multiple supplies can be found by linear combinations of these changes. This gives a mechanism for these entrepreneurs to explore changes in their supply orders and in their production targets, and to adjust these dynamically as they feel appropriate. Okay. Second example, using an economic equilibrium Leontief class model. This is the same model that we have discussed previously, a balanced three-sector economy where we have a primary, secondary, and tertiary sectors, and each one requires exactly the same amount of input from the other, 0.3 million, for each $1 million of output. And we looked previously at a question of what should happen if we have $100 million of consumer demand from each sector. What if this problem was expanded to look at more variations in potential consumer demands? What if the same economy instead had a $150 million demand for primary and secondary sector output, but a $200 million demand for the output of the tertiary sector? Right? How would this change the equilibrium solution compared to the balanced 100 million demand for each? What if these demands have uncertainty? If there's uncertainty of plus or minus 10 million in these values, what is the uncertainty in the total output needed to achieve equilibrium, and so on? How do we address these kinds of questions? Once again, we have multiple consumer demands to consider. The formulation for this is using symbolic constants for our demands. We've walked through this kind of problem a number of times, but I'll do so again just briefly. We can have a general form. We let xi and di be the total supply and total demand of each economic sector. I for primary, so 1 for primary, 2 for secondary, and 3 for tertiary. And in this case, we'll also let bi be the consumer demand for each of those sectors. The general model has total demand written as a sum of a set of internal demands, the demands required by each sector in order to produce output for that sector. These are all dependent on what the supply from those sectors is, the X1, X2, and X3s, and added on to that an external or consumer demand for the appropriate sector. In the cases we've seen before, this last column has been numbers, and we've replaced this with symbolic constants here. And as we've discussed before, the question of economic equilibrium or a balanced supply-demand is found by asking what values of xi will produce this sort of total demands perfectly equal to xi. So the sort of target is, can we replace this with x1, x2, x3 equals this expression? And we've seen how we can formulate this as a matrix problem. This general problem, x's equals these right-hand sides, can be written as x equals ax plus b, with our coefficient matrix of all 0.3s corresponding to this block here, extra constant block of b's, and our variables both on the left-hand side and multiplying the vector. We've also discussed elsewhere how this form can be rearranged into a form of I minus ax equals b. And so if we define a matrix M to be I minus A, as written here, this system ends up being written as MEX equals B, a standard form. Once again, we're looking for an ability to solve this system for multiple different right-hand sides, and the inverse gives us a tool to do that. We have a square matrix, so as long as that matrix opens the possibility for an inverse, as long as this matrix is non-singular, that is, the inverse exists, if we can compute it, then we can plug in whatever set of consumer demands we would like for B and find an answer, a solution to the supply-demand problem. First step, of course, compute the inverse. This should now start being quite sort of familiar to you. You want this to be a very comfortable step. We begin by setting up our block matrix, coefficient block, identity block of exactly the same size, walk through the steps of Gaussian elimination. Here, we're going to add a few scaling steps that aren't part of formal standard Gaussian elimination to make the arithmetic work a little bit cleaner. So the first step, I don't like working with decimals. I'm going to multiply every row by 10 just to move into whole numbers, and that transforms the system into here, making sure that we multiply the identity block also, so we now have 10s in these positions here rather than the 1s that we started with. Then we go through Gaussian elimination, start in the upper corner, eliminate downwards. Not the simplest numbers here, coefficients here, so we have a bit of a fraction to use in the subtraction. We add 3/7 of the first row to each of the second and third, and that will zero out these 3's using the 7. We, of course, get zeros in the first position, -3 plus 3/7 of 7. In the next case, we have 7 plus -3 times 3/7. That's 49/7 minus 9/7, or 40/7. In this case, we have -3 plus -3 times 3/7. This is -21/7 minus 9/7, or -30/7. 0 plus 10 times 3/7 is 30/7, and 10 plus 0 is 10. 0 plus 0 is 10. That gives us this first row. Or sorry, second row here. Because we're using exactly the same coefficient in the third case, and because we have really the same numbers showing up here, we're going to get the same numbers in this row, but in different positions. A -3 operating with 7 gives us a 0 in exactly the same way. This -3 and 3 is going to behave exactly the same way as this -3 and 3, so we get a -30/7 here. 7 and -3, same as 7 and -3 here, giving us a 40. And exactly the same 0 plus 30/7 for this piece. Okay. You can work through the arithmetic more carefully if you would like. We now, before moving on, are going to do another scaling. Everything here is a fraction of 7. That's going to be a little bit annoying to deal with. The numerators are all factors of 10. So let's multiply everything by 7, divide everything by 10, ignoring the first row because the first row is okay. And we end up with 47ths, -37ths, and 37ths becoming 4, -3, and 3, and 10 becoming 7 when we multiply it by 7/10. Same thing in the second row. We end up with -3, 4, 3, 0, 7. Now that things are a little bit more clean, we can move down a row, over a column, one more pivot. To eliminate this -3, we would add 3/4 of the second row. -3 plus 3 is 0. 4 plus -3 times 3/4. That's 16/4 minus 9/4, or 7/4. 3 plus 3 times 3/4 is 12/4 plus 9/4, or 21/4. 0 plus 7 times 3/4 is also 21/4, and 7 plus 0 is 7. This is now an upper triangular form, 3 pivots with zeros everywhere to their left. We're ready for back substitution. For the back substitution piece, here we do not have ones along the diagonal, so we're going to have scaling steps involved. The first, we start with the last pivot. We scale this value by 4/7 to get a 1 in this position. This also has the result of making the pieces in the right-hand block simpler. 21/4 times 4/7 is 21/7, or 3. So we get a 3 and a 3. 7 times 4/7 is, of course, 4. Once we have this, we can now eliminate upwards. To get rid of these -3s, we add 3 times this row to each of these rows. -3 plus 1 is 0. 10 plus 9 is 19. 0 plus 9 is 9. And 0 plus 12 is 12. For the second row, -3 plus 3 is 0. 3 plus 9 is 12. 7 plus 9 is 16. And 0 plus 12 is 12. So this gives us our next 2 rows. Sorry, these here should be zeros in these places. We've zeroed them out. We then move to our next pivot, up a row, over a column. Start by scaling, multiply this row by 1/4, gives us 1, 0, 3, 4, and 3. And once we do this, then we're ready to eliminate upwards. Again, this will be achieved by multiplying row 2 by 3 and adding it to row 1, as outlined here. 1 plus 3 is 0. Sorry, -3 plus 3 gives us 0. 0 plus 0 gives us 0. 19 plus 3 times 3 plus 9 is 28. 9 plus 12 is 21, and 12 plus 9 is 21. That gives us our row here. After elimination with that pivot, we move up a row and over our next pivot. The only remaining thing to do is to scale this entry. Dividing through by 7 gives us 1, 0, 0. 28 over 7 is 4. 21 over 7 is 3. 21 over 7 is 3. At this point, we're in our reduced row echelon form. We have an identity block where the coefficient block was, and when that happens, that means we must have the inverse of our matrix in this right-hand block. Now that we've found the inverse, we are ready to move forward with applying the inverse to solve the problem of interest. Right? Let's first of all tackle this first piece. This is actually a piece we have solved in a previous example. We'll verify that we get the same result. If there is consumer demand of 100 million for each sector, what is the total output that will match supply and demand? We simply insert into this B these consumer demands of 100, 100, 100, and then work through the matrix multiplication of x equals m inverse b. 400 plus 300 plus 300 is 1,000. 300 plus 400 plus 300 is 1,000. 300 plus 300 plus 400 is 1,000. This gives us our result that each sector must produce $1 billion worth of output in order to satisfy $100 million of consumer demand or external demand, as well as satisfying the demands on producing output from each sector. If we move to a second set of demands, a different set of demands, the only difference is in the B vector. 150 demand for primary and secondary gives us 150s in these first two positions. A $200 million demand from the tertiary sector gives us 200. What is the total output now? We see multiplying through 4 times 150 is 600. 3 times 150 is 450. That gives us a total of 1050 plus 600 gives us 1650. You work through the arithmetic, you'll get 1650, 1650 for the second row, and for the third row, 1700. 3 times 150 is 450, plus 450 plus 800 gives us 1700. In this case, the primary and sectors must produce 1.65 billion, while the tertiary must produce 1.7 billion. Interesting to see that the required total output of the tertiary from the secondary still only differs by 50. There was a difference in 50 million in the consumer demands. That's actually the same difference that we see in the total output, even though the overall values increased much more. Adding 50 million in demand for 2 of the sectors and 100 million of demand for another, so a total increase of $200 million overall in consumer demand, has increased the supply values from $1 billion to more than 1.5 billion. So much more overall production, but the differences still have only the difference from the consumer demand. This happens because of the perfect balance between demands internal to the economy. We might then ask the question, what happens if there's uncertainties in this demand? How does uncertainties in demand input the uncertainty in what those final equilibrium values would be. We have already seen how we address uncertainties, how we propagate these into this kind of a problem. We formulate the problem in this way of how does a change in the right-hand side, a delta B, lead to a change in the solution, a delta X. And we can find that by using the inverse. Turns out that delta X simply equals M inverse times delta B. So, variation and uncertainty of 10 in each of the consumer demands, we might represent by putting 10 into here, how into each unit, 10, 10, and 10. How does this propagate into uncertainties? In a very, not surprisingly, when we had hundreds in here, we got 1,000 in all of these units. When we have tens in here, we get hundreds. 40 plus 30 plus 30 is 100. 30 plus 40 plus 30 is 100, and so on. Uncertainties, if plus or minus 10 in consumer demand, leads to uncertainties in plus or minus 100 million in total supply and demand. This has grouped all of them together. You might have decided to try to tackle this separating them out. What would happen if we tried to do that? Well, this might be found by doing something like this. 4, 3, 3, 3, 4, 3, 3, 3, 4. This is our inverse. And let's say we isolated one of the variations to 10. What does this give us? 40 plus 0 plus 0. 30 plus 0 plus 0, and 30 plus 0 plus 0. And what we would actually get if we also did this for the 0, 10, 0 case, we would get 30, 40, 30. And for the 0, 0, 10 case, we would get 30, 30, 40. And if we add these up, 40 plus 30 plus 30 is 100, 30 plus 40 plus 30 is 100, and so on. What this kind of tells us is actually a breakdown of where this 100 uncertainty comes from. Actually, 10 of this uncertainty comes from the actual uncertainty in the consumer demand, and then a balanced 30 of uncertainty in every sector comes from the propagation of that, the necessity of accounting for that uncertainty in the production and the interdependence of the values of the economy, right? So of this final 100 for each of these, 10 of the uncertainty directly comes from the consumer demand, and 90 of it comes from the internal relationships in the economy. Okay, that ends our examples for Unit 4 and wraps up our discussion of Unit 4, focusing on the matrix inverse. Thank you and goodbye.